Hi everybody! So in this video we are going to talk about something called electron configurations. And you might be thinking, what the heck is that? Well, don't worry, I'm going to tell you. So basically, in these first few weeks of this class, what we've really been looking at is atomic structure, right? We know that inside of an atom, we've got protons and neutrons existing inside that nucleus. And then we walked through kind of the history of atomic structure that led us up to Niels Bohr. And Niels Bohr told us that electrons exist in these circular orbits that he called energy levels, and they reside in these circular orbits around the nucleus of an atom. And then Schrödinger came along and said, well, that's actually not true. They don't move in circular orbits. Electrons do have some amount of energy, but they kind of move randomly around the nucleus of an atom, and therefore it makes them really, really hard to find. So Schrödinger said we can't really ever know the exact location of an electron, but we can make a pretty good guess using probability calculations. We can also make pretty good guesses about where these electrons exist by writing out these things called electron configurations, which help us kind of locate where electrons are likely to be found within an atom. So these electrons, they do exist in these energy levels. They have some sort of energy associated with them. And within those energy levels, there are these things called sublevels. These sublevels are composed of different types of what we call orbitals. And what actually is an orbital? All an orbital is an area of electron density. What this means is these are areas where you are likely to find an electron, or find some electrons. If you're looking at that picture on the right-hand side, what that kind of shows you is that there are 4 different types of these sublevels, of these orbitals, and they range in order from not so crazy of a shape to pretty insanely shaped. These orbitals do exist in 3-dimensional space, which makes sense because we exist in 3-dimensional space. And we can use these locations, we can use these orbitals to kind of classify probable locations of electrons. And we do this by writing out electron configurations. I'm gonna run out of space. Electron configurations. So there are 4 different types of orbitals as seen in that picture. S, P, D, and F are the names that they go by. Every one of these orbitals can hold 2 electrons. But there's different numbers of these orbitals in each of these sublevels. But if you take a look at S only has 1 orbital, just this spherical looking one right here. So within an S orbital, within an S sublevel, there's only 1 orbital, which means the maximum number of electrons that can be found in an S shell is 2. Then you go to P. P has 3 orbitals in its sublevel. So if each of those orbitals can hold 2 electrons, the 3 orbitals each holding 2 electrons means you can have 6 electrons held in P orbitals. So, excuse me. So if I take a look at this table right here, what I'm kind of doing is just taking this number of orbitals and multiplying it by 2. Each orbital can hold 2 electrons. So S can hold 2, P can hold 6, D can hold 10 electrons max, and F can hold, 14 electrons max. We really will not deal with F orbitals in our class. We will talk about D orbitals, but we won't deal with them too much. Really, we're going to be dealing with the S and the P pretty heavily. So these are the different shapes of the orbitals. I won't expect you to be able to draw them other than S and P. S and P you should be able to recognize. The other ones are kind of gnarly. But what can we actually do with these orbitals? What information do they give us? What we can do is we can draw something called a ground state orbital diagram, and that is represented in this little box right here. What this is showing you is like a visual representation of the energy that these different electrons have. So remember that everything is designed to be lazy, right? So electrons always want to fill into the lowest energy level that possible first before trying to go to higher energy levels, because why would they go to a higher energy level when they can be low in energy? So what this is showing is as you move up in this direction, you are increasing your energy. What I'd like you to do is just take a second to kind of analyze this picture here and see if you can answer number 4. What you're doing is basically breaking down this diagram. What do you think each piece of this diagram is showing you? And you're going to match up the letter. So for instance, I'd match up letter A with whatever I think this is. If I think it represents a single electron, I would write in a Roman numeral I here. So take a second, try to analyze this diagram, pause the video, and come on back to see how you do. Okay, so if I take a look at this diagram, first thing that I notice is that there's these arrows up and down in each of these boxes. Remember here that we're talking about electron location. So what that kind of clues me into is I think that each of those arrows represents an electron. So what that means to me is that here for letter B, I see the single arrow. That must mean it is a single electron. So I'm going to say that those two match up together. Which means that if I have 2 arrows, like I see in letter C, that must be a pair of electrons. Now it says pair of electrons with opposite signs. So what do you think the sign could be referring to? It was probably referring to the direction of the arrow, up versus down. So that means that C must be II. Okay, my next ones. I've got a singular box and I've got 3 boxes that are all put together. So my options here are an atomic orbital, which is a region of space where an electron is likely to be found, a sublevel, a set of orbitals having equivalent energy, or an electron configuration. So I noticed that those electrons, those arrows, are residing within those boxes. So that kind of clues me in that they are a space where I can find electrons. Ooh, area of electron density. That sounds like an orbital, which means that each of those boxes must be representing an atomic orbital. So A must be III. So if I take a look at D and I zoom in on that set of 3 here, I notice that all of these are level with each other. And we said that as we go up higher on this diagram, we're increasing in energy. So if these 3 boxes are at the same place on this energy diagram, that means they must be a sublevel, a set of orbitals that has equivalent energy, IV. So last but not least, that set of numbers and letters at the bottom must be an electron configuration. So that's exactly what that is. Here's an electron configuration. I've copied it for you below. What this is really showing you is it's kind of showing you like, basically like the addresses of the electrons within an atom. Where do these things reside? Where do they live? So the energy levels are those numbers. This doesn't change from kind of what we were looking at in the Bohr model, right? Energy level 1, n equals 1, n equals 2. That's not changing here. So the energy levels must be represented by these large numbers here, 1 and 2. Sublevels. Sublevels are those orbitals that have equivalent energy, right? So if I'm taking a look here, I have an S is a sublevel, an S is an orbital, so I'm going to circle that one. I see another S here, that must be another orbital, so I'm going to circle that. And then P is another orbital, so I'm going to circle that thing. Lastly, I'm looking for the number of electrons. So the last thing that's represented in here is these numbers right here that are written as superscripts. These represent my number of electrons. So what is this actually telling me? It's telling me how many energy levels my electrons can be found in. Here I can find electrons in the first and second energy level. It tells me what type of orbital these electrons are present in, and therefore I would know the shape of those orbitals. So I have S and P. And lastly, it tells me the number of total electrons that are present within this atom. What we're assuming here for all of ours is we're going to assume that our atoms are neutral unless told otherwise. So if I count up the numbers that I have in my boxes, 2 plus 2 is 4, 4 plus 4 is 8. That means I must have 8 total electrons represented. Oh, hello. It must be represented in my electron configuration. So how could you use this information to determine the identity of an element or vice versa? Okay, so I know that I have represented 8 electrons in this atom. We're assuming that everything is neutral. Neutral is referring to charge. So if I have 8 electrons, I must also have 8 protons. How can I identify an element based on its number of protons? Oh, easy. That's atomic number. All I have to do is look on the periodic table. So if I look on my periodic table, the element that has 8 protons, or an atomic number of 8, is oxygen. So this must be the electron configuration for oxygen. I'll let you pause the video here and try to write your own explanation for letter E using what I just talked about. So these are all ground state orbital configurations, or ground state orbital diagrams for 4 different elements. When we're referring to ground state, what are we actually referring to? It's referring to when our atom has its electrons arranged in the lowest possible energy state. That is in its ground state. So how can we decide how we're actually going to take these electrons and kind of organize them in this diagram, and how the heck can we write these electron configurations for these different atoms? Well, there's some rules that we have to follow, and the first rule is called the off-bow principle. So the off-bow principle basically tells you how you're going to fill these electrons in. Everything's designed to be lazy. So what that means is we have to start filling lowest energy first to highest energy. Number 6 has a set of questions in it that I'd like you to try and use these ground state orbital diagrams to kind of figure out what the off-bow principle is actually telling you. Go ahead and answer number 6 and go ahead and answer number 7. Pause the video and then check in with the answer key to see how you did on those. Okay, so after off-bow principle, there's another rule that kind of tells us how we're going to draw ground state orbital diagrams and electron configurations, and that other rule is called the Pauli exclusion principle. What this says is that if you have electrons that are in the same orbital, remember that every orbital can have 2 electrons. So those 2 electrons must have opposite spin signs, 1 positive, 1 negative. So based on the examples of these arrows here, what do you think it means to have opposite spin signs? Well, it would make sense that the only thing that's really opposite here is the direction of those arrows. So if you're going to fill electrons into into a ground state orbital diagram, what you need to do is make sure that those electrons have opposite spin signs when you are filling. The last rule that we have to follow is called Hund's rule. So there's 2 important parts to Hund's rule. They're represented in question number 8. I've given you the ground state orbital diagram for oxygen here, so go ahead and again pause the video, see if you can pick out what Hund's rule says, and then I'm going to go through one of the practice problems with you in part 3. Okay, here we go. Hopefully you figured out off-bow. You've got Pauli exclusion. You got Hund's rule now. We're going to put it all together and we're going to draw some ground state orbital diagrams. We're going to write some electron configurations. Here we go. Okay, let's start out with sulfur. The first thing we need to do is we need to figure out how the heck are we going to decide how many electrons are going in to this ground state orbital diagram? Oh, all my atoms are neutral. Okay, so all my atoms are neutral. I got to have the same number of protons and electrons. So what I can do is take a look at my periodic table and find sulfur, which is right here, and its atomic number is 16, meaning it has 16 protons. That means if it's neutral, it's also got 16 electrons. So I know I need to fill 16 electrons in. I'm going to write myself a little note up here to remind myself that I need 16. So I know that as I go up in energy, this is the direction that I am going to fill from, lowest energy to highest energy, because that's what off-bow principle tells me. So I know that 1s must be the lowest possible energy orbital. So I'm going to put an electron into the 1s orbital. The way that I draw my electrons in ground state orbital diagrams is I draw them with like half arrows like this. I think it just makes it a little easier. It truly doesn't matter. If you want to draw the full arrows out, go for it. So I've got one electron in the 1s orbital. Where am I going to put the next one? Well, Hund's rule tells me that I have to completely fill up an orbital before I can move on to the next one. But 1s only has one orbital, which is great, awesome. I can put my other electron there. Now I have to consult Pauli exclusion principle. This tells me that my electrons must have opposite spin signs when filling into the orbital diagram, so therefore, these electrons must have one up, one down spin. All right, I got rid of 2 electrons, 14 more to go. The next energy level that I'm going to fill into is 2s, because I see that it is lower in energy than 2p as represented by the energy diagram. So I'm going to put 1 electron in 2s. I don't have anything else to worry about in 2s because I only have the 1 orbital, so my other electron must go also in the 2s orbital, and it needs to have a spin down, so that way I have 1 of each spin. Okay. 4 electrons down, 12 more to go. Now I have to deal with P. So off-bow principle tells me next energy level up is 2p. So I'm going to put 1 electron in this first orbital here. Now the Hund's rule tells me that I have to put 1 electron in each of these orbitals before doubling up. So that means is I'm going to put 1 electron in this first 2p orbital. I need to put 1 electron in this second 2p orbital and 1 electron in this third 2p orbital. Now that each orbital has 1 electron, now I'm free to double up. So why would it do this? Why wouldn't I just double up into 1? It's all about repulsion. So think about how these electrons are oriented. Within, I'm going to draw it down here. So within a p orbital, you have this one right here. This I'm going to call, let me draw out my little diagram here. Let's say that I'm oriented in 3D space. This I'm going to call my x-axis. This I'm going to call my y-axis, and the one that's coming out towards me, actually, nope, I did that wrong. This is going to be my x-axis. The one that's coming out towards me is going to be the y-axis. The one that's going up is going to be the z-axis. Doesn't actually matter as long as you're oriented correctly, but this is how I'm going to draw this one. So if I have something going up and down in the plane, that corresponds to the z-axis. So this is called pz as an orbital, p sub z. This is one of the p orbitals. But there's another one. There's another one that lays right on top of it, and this one is in this direction. This is my px orbital. Then I have one last orbital that's coming out towards me, and that's the py orbital. So this part of the orbital is coming out towards me. I'm going to draw this part of the orbital going like this, showing it's going back into my paper. And this will be py. So why would my electrons want to fill 1 electron in each of these orbitals before doubling up? It's all about repulsion. if I can take one electron and put it here, and one electron and put it here, and one electron and put it here, what I'm doing is I'm maximizing the space between my electrons. This is going to minimize the repulsion between these electrons. So that's why we need to put one in each before doubling up. So back to my ground state orbital diagram, if I come back up here, I still have more electrons I need to fill because I need to get to 16 electrons. So now I can start doubling up. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total now I have 10 electrons represented in my ground state orbital diagram. I still have 6 more to go. Okay, next. Still going up in energy, back to off-bow principle. Next orbital that comes up is 3s. So I'm going to put 1 electron spin up. Pauli exclusion principle tells me the next one's got to be spin down. I've still got 4 electrons to go. Okay, now I go up to p. Put 1 electron in 3p. But I still have to make sure, according to Hund's rule, there's 1 in each before I double up. Put another here, put another one here. And now I have 1 electron left. So it doesn't actually matter where you put that electron. All of the p orbitals, remember, are equivalent in energy. It's just kind of like traditional to put it in this first box right here, but quite honestly, it doesn't matter. It could have been in any of those p orbitals because they are all equivalent in energy. But this is the final ground state orbital diagram for sulfur because now all of our boxes are filled according to the 3 important rules that we need to know when drawing these out. So how can I take this ground state orbital diagram and turn it into an electron configuration? All I do is take my energy levels, my orbitals, and my number of electrons and write them out in order of increasing energy. So again, I start at the bottom. My orbital in lowest in energy is 1s, so this must be what I write first. How many electrons are in this orbital? 2, as dictated by my picture. Next would come the 2s orbital. How many electrons are in there? 2. All right, now I've got the 2p orbital. How many electrons are in here? I have 2 in each of these boxes, meaning I have a total of 6 electrons in the 2p orbital. Then I've got 3s, there's 2 electrons there. And then I've got 3p, how many electrons are in there? Only 4. So this sublevel is not filled. Okay, go ahead and try silicon and neon on your own. Check in with the answer key, see how you do. Okay. So, I know that this seems a little bit confusing. It seems like, well, how the heck am I just supposed to look at something and figure out the filling order? Well, there is a little cheat sheet that you can use. I kind of want you to understand how to do it on the periodic table, so I'm actually going to talk you through that during class. But for right now, you can use this little graphic. This little graphic is a cheat sheet filling order. What you do is you follow the arrows as you start with the lowest energy, which is 1s, and you follow it through to the highest energy orbital, which is 8s. So what this is showing is I start here, I follow along on this little curved arrow until I get to the next orbital, and then I keep going, I fill in on the next orbital, keep going, fill in on the next orbital, and so this is showing you the filling order. It's showing you start with you start with 1s, come around, next would be 2s to fill, 2p to fill, 3s to fill, 3p to fill, 4s to fill, and then notice you get here, and now you've got d orbitals. Remember, how many electrons can we fit in a d orbital? There's 5 orbitals. There's 5 d orbitals in the sublevel. Each orbital can hold 2 electrons. I can fit 10 electrons in that d orbital. So let's see if we can make some use of this. Getting used to filling this graphic. So electrons fill from lowest energy level to highest energy level. And don't forget that, very key. We're going to try and write out the electron configuration for strontium to help us out. So strontium is Sr. If I head to the periodic table, strontium shows up right here. Its atomic number is 38. I know I use strontium for a lot of my examples. It's a great element. That's why I pick it. All right, so strontium's got 38 electrons. I need to figure out how I can possibly get 38 electrons in my electron configuration. So let's start out with the 1s orbital. I am starting with 1s because it's lowest in energy. How many electrons can fit in an s orbital? 2. So I'm going to put 2 electrons in there. Great, now I've got 36. Okay, minus 2, 36 electrons. All right, 2s is up next. I can fit 2 electrons in that s orbital. Great, minus 2, I got 34 left. 2p is next. How many electrons fit in a p orbital? 6 max, so I've got 2p6. Subtract 6 out. Oh, let's see if I can do some quick math. I think it's going to be 28. Yes, it is. All right, next on my list, sorry, I've got 1s. I went over 2s. I went to 2p. Next is going to be 3s. So 3s, how many electrons fit there? 2 minus 2 gets me to 26. All right, keep it circling around. Next up is 3p. 3p, how many can I hold there? 6. Subtract that out. I've got 20 electrons left to fill. Whew, okay, keep going. What's next? 4s. How many electrons can fit in 4s? That's right, 2. Subtract out 2 more, and I've got 18 left. All right, I'm going to restart this little count so I don't run out of space. All right, so I've got 18 electrons left to fill in. What comes next? Exciting. 3D. Ooh, d orbital. Yay. Okay, how many electrons can I fit in a d orbital? Earlier we said 10. So this is going to be 3d 10. I'm going to subtract all of those out, and I've got 8 left. What comes next in the filling order? 4p. So 4p comes next. I can fit 6 electrons in there, minus 6, and I've got 2 left. Ooh, how convenient. The next energy level to fill is 5s. So in here, we've got 5s, and I can fit 2 electrons, which is exactly how many I have left. No more electrons left to fill, and this is the ground state electron configuration for strontium. That's a lot. A long process. That's a lot to write. I bet you're thinking, gee, I wish there was a little bit of a shorter way to write this electron configuration. Guess what? I'm about to blow your minds. There is. It is called the noble gas configuration. This is a quicker way to write electron configurations. So to speed this up, we can take a look at the noble gas column on the periodic table. So if I take a look at the periodic table, the noble gases show up on the very far right-hand side, starting with helium, neon, argon, krypton, that column right there, that is the noble gas column. That's their family name. All of these elements have similar properties that have grouped them together in that last column, and we call them the noble gases. So your first step to writing noble gas configuration is to figure out which noble gas is in the period before, key here, before the element that you're writing the electron configuration for. So if I find strontium, strontium shows up in the 5th period of the periodic table, which means I'm looking for the noble gas in the 4th period of the periodic table. If I backtrack, that's going to be krypton, atomic number 36. So that first step tells you to write that noble gas in brackets. So we're going to write KR in brackets, just like this. Essentially what this is doing is I'm saying that I am accounting for all of krypton's electron configuration in these brackets. Krypton, if you did the electron configuration for it, would end up being, let me go back to strontium, everything here. Krypton's electron configuration is exactly all of this, ending at this space right here. So the bracket KR takes care of all of that highlighted information. It's saying that I'm accounting for all those electrons just by calling this noble gas configuration. So step 2, you're going to finish the electron configuration by removing everything that's included in the noble gas configuration. So what that means is you're always starting with an s orbital. Why? On the periodic table, there's some organization that we're going to take a look at. And essentially, those first 2 columns of the periodic table, groups 1 and 2, starting with hydrogen and then beryllium, that's called the S block. Why? Because their electron configurations end there. They will end with some energy level in an s orbital. So in our electron configuration, notice like that I said, krypton takes care of all of this. All that's left is this piece of the puzzle, 5s2. So the way that you can write the noble gas configuration for strontium is by taking into account krypton's electron configuration, then finishing it off, 5s2. Okay, I'm going to have you pause here. Do not do these practice problems yet. I want to walk you through how to actually figure out electron configurations using the periodic table before trying to go through this process using the cheat sheet and then doing noble gas configurations. So just take a pause here. You can get some practice with electron configurations with the practice sheet that's posted in the resources folder, but we are going to talk more about electron configurations in class together.